Okay, so welcome to this video to correct the matter test. So what I expect you to be doing is using a different coloured pen to mark yourself, and also doing two other things. So adding in some corrections in a different coloured pen, and also to write down other correct answers which were worthy of credit. So if you do that, you will be improving at a far greater rate than if you just put a tick or a cross and how many marks you got. So do take the time to pause this video when you need to add in other correct responses and corrections. So question number one, in winter solid ice forms on a car's rear window. There's a picture. The glass window contains an electrical heating element. A heating element is just a piece of wire, or maybe sometimes it's a bar that can heat up. You will often come across that word element in physics exams. Use the particle model in figure 2 to describe how the heating element causes the arrangement of ice particles to change as the ice melts. So, picture of the solid here, then melting, then a picture of the liquid here. You should include a description of how these particles are arranged in the solid, ice and water. So this is what I said. I'll read it because my handwriting isn't great. In a solid, the particles are arranged in fixed ordered rows and are touching, whereas the particles in a liquid are in no particular order but are able to slide over each other. So the device that I've used there, and I've highlighted it, is whereas. So I started off talking about the particles in a solid, then I used the connective whereas, and then I put in the contrasting things about the gas, the liquid, excuse me. So using whereas in these answers is really good. Energy from the thermal store in the element is transferred to the ice via heating. The temperature of the ice increases until 0 degrees, and so does the kinetic energy store of the solid particles. At 0 degrees, the ice changes state to water, and the energy from heating is used to increase the potential energy store of the particles at a constant temperature. So it's possible to add in a lot of correct science here. So after you've done the basic description of the arrangement of particles in ice and water, then you have to kind of talk about what energy transfers are taking place and the effect of those energy transfers on the energy of the substance. And substances can store energy, if you remember, in two ways. The particles, once heating is done and energy is put into a substance, can start to move around faster, and that's increasing the kinetic energy store of the particles. Also, to remember, and it's really good to remember this, when the kinetic energy store of the particles is increasing, the temperature must be increasing. Related to that, if the temperature is not going up but heating is happening, that means that the energy must be going into the other store that the particles can hold energy in, which is called the potential store. And when the potential store is increasing, that is a sign that it can be changing state. Bonds can be being broken, and they can be particles can be separated out, and energy is needed to do that. So let's go to the mark scheme. So current in the wire causes heating. I didn't highlight that, so that's something I could add in. Increases temperature of the metal wires and the ice. I did say that. Arrangement of the particles is regular. I said ordered. That would, two words to the same thing. Particles vibrate about a fixed position. I said that. In terms of melting, they have said that the internal energy of the ice increases, and that increases the temperature to melting. So the internal energy is important to understand. If you take a look at a particle, the internal energy of that particle is the sum, adding together the sum of the potential energy and the kinetic energy. So they've said that increasing the internal energy means that the particles vibrate faster. I didn't say that, so there's credit if you did, and I should add it to my script. The particles vibrate fast enough to break free from the strong bonds, so that there's good marks for that. Therefore the arrangement becomes irregular. So in a liquid the arrangement is irregular or not ordered, and the particle movement is random. So there's a lot of extra stuff, so I think that I could improve my response by talking about on melting the particles would be firstly vibrating faster, and then the bonds between the solid particles would be broken. So a lot to that question. Let's carry on. So next one. A car manufacturer tests different heating elements by measuring how long it takes ice to melt. During the test, variables must be controlled. Identify 2 control variables in the manufacturer's test. Tick 2 boxes. Now this word or phrase, control variables, means things that you need to keep the same so that your results are valid. So, you know, at key stage 4, it's wise to avoid the term fair test, but it's essentially the same thing with a different wording. So the control variables, things that must be kept the same to get results that are valid. Well, the colour of the car doesn't make any difference to the heating of the element. The current in the heating element does. So I selected that one here, because if the current's higher, the wire's going to get hotter and more heating's going to happen, and then it wouldn't be fair to compare results. You wouldn't get valid results. So the mass of the ice is the other control variable, because if you have more ice for a heating element to heat up in one case compared to another, well, it's obviously going to need more energy to melt that ice, and so you couldn't compare your results in those cases. The size of the car doesn't make any difference. Maybe the size of the heating element does, but certainly not the size of the car. And the time taken for the ice to melt. So that is not a control variable. That is actually probably you would likely have that as a dependent variable, which is the variable you would be measuring. Okay, part C. Some of the energy supplied by the heater causes the ice to melt without the temperature of the ice increasing. What is the name given to the energy supplied by the heater? So when you're getting a change of state, so you're going from a solid to a liquid, or a liquid to a gas, or vice versa, you are talking about latent heat. Heating that's happening without a measurable change in temperature. If you're going from a solid to liquid, that is called, the amount of energy you need is the latent heat of fusion. And just an extra layer of detail, if you see the phrase specific latent heat of fusion, you are specifically interested in heating up 1 kilogram of substance, so it changes state from a solid to a liquid, or the energy you'd get if a liquid went to solid and heating happened in the other direction. Okay, when the heater is supplied with 120 joules of energy each second, the internal energy of the ice increases by 45 joules each second. Use the following equations to calculate the efficiency of the heater. Efficiency is the output energy divided by the input energy transfer. So 45 joules went into the ice each second, but the heater, the heater supplied, put into the ice, or the heater supplied 120 joules. So that calculation gave you 0.375, and because it says to 2 decimal places, the 5 here tells you that you need to round the digit before it from 7 up to 8. So 2 points here. You could just write 0.38 because that's a decimal efficiency. So decimal efficiencies are always numbers between 0 and 1. If you don't have numbers in that range, you're wrong. You could also times it by 100 and get 38%. And because it's you know, the percentages, percentage efficiencies are also valid ways to give efficiencies. So let's have a look. Where is my mark scheme? My mark scheme is here. So 0.38. There you go. So 1 mark for that, 1 mark for that calculation. Crack on. Diagrams X, Y, and Z show how the particles are arranged in 3 states of matter. Which one of the diagrams X, Y, or Z shows the arrangement of particles in a liquid? You should have said Z. They're touching, they should be touching. You can see there's a bit of an error in the picture there when they're not quite, but they should all be touching, and they should all be in a regular way. Which one of the diagrams X, Y, and Z shows the arrangement of particles in a gas? It's X, because the particles have a large separation between them. The other two should show touching. Draw a ring around the correct answer in each box to complete each sentence. In the gas particles are moving randomly. 1 mark for that. In a solid, the forces between particles are stronger than the forces between the particles in a liquid. So yeah, the general rule for this one is that the stronger the closer particles are together, the stronger the bonding is in terms of the particle model. And if you have a very strongly bonded particle, you need more energy to break those bonds to change their state. So it would take more energy to go from a solid to a liquid, because the particles are closer to, on average, closer together than it would to go from a liquid to a gas. So the particle the picture below shows a puddle of water in the road after a rain shadow. Here's the puddle. Part 1. During the day, the puddle of water dries up and disappears. This happens because the water particles move from the puddle to the air. What process causes the particles to move from the puddle into the air? Draw a ring around the correct answer. The answer is evaporation. Condensation is when you've got gas going to a liquid, and radiation might be powering radiation is something that can put energy into the water. And it might affect the rate of evaporation, but it's a process of energy transfer and not a particles changing state. So evaporation, just in passing, is different to boiling, because evaporation only happens at the surface of liquids, and it doesn't happen at boiling point. It happens far beneath boiling point. Okay, part 2. Describe one change in the weather which would cause the puddle of water to dry up faster. So an increase in air temperature, an increase in wind speed, or being less humid. So what actually happens in evaporation is particles in a liquid at the surface would have a range of energies, because they're all kind of like bumping into each other and colliding, and a certain proportion of those particles will end up accidentally having a slightly higher amount of energy on average to the others. So these particles need less additional energy to change state, and of course air is flowing across the surface of our puddle. Especially if it's windy, you get a lot of air moving past the surface of that liquid. So what happens is that air particles actually will collide with water particles at the surface and transfer some of their energy to these water particles, which already have a higher amount of energy than the average water particle. and what this can do in some of their cases is it can give them enough energy to change state. If your air is hotter, it means that the air molecule will be moving around faster, so it will have more energy to give to the particle at the surface of the water on the collision. Also, if the wind is going faster, this particle will also be carrying more energy, so it can collide and transfer that energy, or more of that energy into the water particle at the surface, so you'll get more changes of state. So another point to make is you could say less humid. So humidity is a measure of how much water vapor is in the air, and if there is less water vapor in the air, it's easier for particles to evaporate. Question 3. Two students investigated the change of state of stearic acid from liquid to solid. They measured how the temperature of stearic acid changed over 5 minutes as it changed from liquid to solid. Figure 1 shows the different apparatus the two students used. So the liquid is always in a beaker. Student A's got a temperature probe, and it can measure to a resolution of 0.1 of a degree centigrade, whereas the thermometer, which student B has a resolution, the lowest thing it can measure, which isn't 0, of 1 degree centigrade. So two advantages of student A's apparatus. So student A's measurements had a higher resolution. That one's correct. So a higher resolution is the lowest non-zero number a piece of measuring apparatus can record. A higher resolution means that that number is finer. It's smaller. So we can measure to 1/10 of a degree here, but we can only measure to a whole degree here. Student B is more likely to misread the temperature. That's true because if you look at the level of the liquid in the thermometer with your eyes not level to the scale, you could, if you're a little bit too low, look up at the surface of the liquid in the thermometer and measure that at 75 if you're being careless. If you're a bit taller and being careless and you look down at the liquid at that in that thermometer, it is also possible to get a result or record a result of 74 degrees. So you can't get this line of sight problem with the data logger because the numbers are just the numbers, 74.2. So 1 mark for each of those. Shouldn't be remove the thermometer from the liquid each time you took a temperature reading. What type of error would this cause? Tick 1 box. Is it systematic, a random error, or a 0 error? So if you take the thermometer out of the liquid, the problem is that the bulb where the liquid is, where your thermometer is measuring from, will be no longer in the liquid. It will be measuring the temperature of the air. And so if the obviously the stearic acid is being heated, so the bulb would start to cool. You don't know how much it would cool down by each time the student took the thermometer out of the liquid. If she took it out for a longer time, then the temperature would drop a lot. If the student took it out for a much shorter time, the temperature might not drop as much. So because you don't know how much it's going to drop by, you can't say it's a systematic error. Remember, systematic errors, you know the direction of the unwanted change and you know the amount of the unwanted change, so you can correct for it. But in this case, you don't know how much the temperature is going to drop by. It might be a little bit or a lot, so it can't be systematic. A random error is, a 0 error is when your results are not what they should be because your measuring apparatus doesn't say 0 when it should do. So that is not indicated at all here, because both of the pieces of apparatus are up in the 70s, so there's no indication it's got anything to do with the zero error. So the result here is a random error. Okay, next one. Now, I'm slightly baffled by this one. So the temperature, what was the decrease in temperature between 0 and 160 seconds? So I did this as best as I could. I measured off 63.8 at the start, and 160 seconds later I measured it 55.6, and that got me 8.2 degrees. So I checked the mark scheme, and the mark scheme said if you had done it super properly and measured to exactly the right squares, it should be 8.4. Okay, I've double checked it. I still think it's 8.2. I'm willing to be shown that I've done it carelessly. The mark scheme still says 8.4. It might be a photocopying error. It definitely hasn't scanned back in a way that you can see it clearly here. So for me, I'm trying to zoom in there, but still you can see that you can't really see the little lines. It hasn't come out perfectly. So 8.4 was the answer. I don't know. I did it as carefully as I could, and I got 8.2. The key point is here, when you take read off of graphs, try and do it as carefully as you can. So the read off here I made 63.8, and the read off here 160 seconds later when I measured across the ruler, I got that 55.6, and I double checked it, and I don't think my read offs were wrong, but essentially I wouldn't have got the marks because I didn't get 8.2, which is sorry, I didn't get 8.4, I got 8.2. So again, how long did it take, how long was the time it took to change state? So that's the flat bit of the graph, so you had to measure the length of the time in the flat bit of the graph, and my read-offs got, well, it finished at 920, which is like this point here, and it started, according to my read-offs, at 160. So that gave you a difference of, well, I made it 160. They say one square difference, so they made it 640. So again, I'm 1 square out, but in this case they've been a little bit nicer and they've given me the mark because I'm between 730 and 780. So give yourself marks based on what you got. Part E. Calculate the energy transferred to the surroundings as 0.40 kilograms of stearic acid changed from liquid to a solid. So the specific latent heat of fusion of stearic acid is 199,000 joules per kilogram. This is the equation that you needed to recall. So the energy is always equal to the mass times the specific latent heat. So the mass has to be measured in kilograms, and the specific latent heat needs to be in joules per kilogram. So E equals m times L. My E was 0.4, my L was 199,000. I times them together, I got 79,600 joules. That was right. So 1 mark for the substitution, 1 mark for the right answer. After 1,200 seconds, explain the temperature of the stearic acid continued to decrease. Explain why. Well, going up here, you can see after 1,200 seconds, it was still at over 50 degrees, which is higher than room temperature. So I said that the temperature of the acid was above room temperature, and so it will continue dropping in temperature. I probably could have gone a bit further and said until it reached room temperature, but you needed to say that it was above room temperature, and it would keep dropping. The temperature would keep dropping until it got to room temperature. Okay. Question 4. Solids, liquids and gases are 3 different states of matter. Part A. Describe the difference between the solids and liquid states in terms of the arrangement and movement of their particles. So, in a solid, particles are in fixed rows and vibrating about fixed positions, whereas, that word again, whereas, so I'm now going to go and talk about the situation in a gas because I've already done the solid one. Whereas in a gas, particles are moving at a range of speeds. That's definitely always vital when you're talking about the motion of particles in a gas. They're moving at a range of speeds and in random directions. So please, please, please take that on board about the motion of particles in a gas. Just learn it. Particles in a gas are moving at a range of speeds and in random directions. Particles are touching in a solid, but are now that's wrong. Are separate in a gas. So my brain switched off there, and that last word should be gas. Alright, so particles are touching in a solid but are separate in a gas. So please don't be sloppy like me. I think I was listening to a podcast as I was doing this, and it didn't do me many favours. I've made a silly slip, used the wrong word, so that would have been me being punished. So, what is meant by specific latent heat of vaporization? So, a couple of things to focus on here. The word specific means that you're talking about 1 kilogram of substance. So there's one mark for that. And vaporization means that the state change that you're talking about is going from again, I've made a mistake. I said a liquid to a solid, and that's incorrect. It should be a liquid to a gas. So I would lose 1 mark. I should only get 1 mark out of that. So please give yourself a mark if you said you're talking about 1 kilogram of substance, and give yourself a mark if you said vaporization means you're talking about changing a state, going from a liquid to a gas or a gas to a liquid. I should only get 1 mark out of 2 for this. So going back to the mark scheme, just so you could see over here, I think. Amount of energy required to change the state of a substance from a liquid to a gas, and you're talking about 1 kilogram. So this bit here. Good. Next one. When a kettle boils, 0.018 kilograms of water changes to steam. Calculate the amount of energy required for this change. So, specific latent heat of vaporization of water is 2.3 times 10 to the 6 joules per kilogram. So again, E equals m times L. M is your mass, which is this number here, and it's already in kilograms, so you don't have to convert. The specific latent heat of vaporization is there, and it's already in joules per kilogram, so you don't have to do any conversions. You times them together, you get 41,400. 1 mark for the substitution, 1 for the one for the right answer. So, part D, the graph shows how the temperature varies with time for a substance as it is heated. The graph is not drawn to scale. Explain what is happening in the sections A, B and BC of the graph. So AB, you should have said it's at a constant temperature because the substance is changing state, and it's the first time the line's gone flat. So that tells you that, you know, here's the second time. So the first change of state when you're heating something up will always be a solid to a liquid if there's 2 flat parts of the graph, and you're talking about the first one. So in the second part, the temperature is increasing, so from B to C the temperature is increasing, but it stops increasing when you get to point C. So C must be the boiling point. So going to the mark scheme, so AB, changing state from a solid to a liquid, or melting, which is this bit here, at a steady temperature. So 1 mark for each. BC, the temperature of the liquid rises until it reaches boiling point. So give yourself marks for that. Remember, you should be adding in things that you didn't get in a different coloured pen, or writing down other ways that you could have got marks. Back to this one. So, balloon filled with helium gas in this picture. Describe the movement of the particles of helium gas inside the balloon. So, random. You can see the directions are in no particular direction, so that's random. And the length of the arrow, in this case, refers to the speed, and you can see that the lengths are all different because particles in a gas move at a range of different speeds. They're kind of all bumping into each other and transferring energy, so occasionally losing a bit and occasionally gaining a bit. So, next one. What is the name given to the total kinetic and potential energy of all the particles of a helium gas in a balloon? So that is the internal energy. So, next one. The helium in the balloon has a mass of 0.00254 kilograms. The balloon has a volume of 0.0141 meters cubed. Calculate the density of helium. Choose the correct unit from the box. So, this symbol here, remember, is the Greek letter rho, and it means density. Density is mass divided by volume. So, I have my brain switched off here, but luckily I caught myself. You need to put your mass on the top line, which in maths is called the numerator, and you need to divide it by the volume, which is this number here, and the thing on the bottom of a fraction is called the denominator. So when you do that, you get 0.180, and the unit is kilograms / meters cubed. And remember, you would say that as a scientist, kilograms per meters cubed. Okay, you have divided mass by volume, excuse me, so the unit ends up being the unit of mass divided by the unit of volume. 2 marks for doing the substitution and getting the right answer, and 1 mark for getting the unit right. So, final question. The student wants to calculate the density of the 2 objects shown in the figure below. So, a metal cube and a small statue. Describe the methods that the students should use to calculate the densities of the 2 objects. So the hard thing about this 6 marker is to go through 2 methods in quite like 6 minutes of time. So I always recommend describing methods in numbered lists. Okay, so you can see that I've done that, and I've got 2 subheadings, one for metal cubes, one for the metal cube, and one for the small statue. And you can see that I'm keeping each point in my numbered list in what we call the imperative. So that's when we say do this, do that. So I'm not trying to be clever, it's not an English exam, I'm not using flowery sentences. I'm speaking in the imperative. Do this, do that, measure this, use that, measure this, record that. So, metal cube. You measure the length, width and height of the cube with a ruler. Use the length, width and height, multiply them together to calculate the volume. Measure the mass using a mass balance. It's really important that you don't use the word scales for measuring the mass of something. Okay? Always in a physics test, if you're measuring the mass, say you're doing it with a mass balance. Step 4, use rho equals m divided by v, which refers to density equals mass divided by volume, to calculate the density. So, for the small statue, you don't have a regular shaped object, so you need to measure the volume a different way. So, measuring the mass is the same using mass balance. So step 2, place the small statue in a displacement can. That's another name for a eureka can. I might just see if I can so remember, a displacement can looks like this. It's essentially just a container with a spout, and you fill it up to just beneath the spout with water. When you put in an object, the level of the water rises. A scientist would say the water is displaced, and the amount of displacement is measured by how much water falls out of the displacement can, and you can collect that into the measuring cylinder. And the volume of water collected will be the same as the volume of the object put into the can. So that is a displacement can. It's sometimes called a eureka can, but it's essential that you talk about that in the right way. Place a small statue in the displacement can, collect the water using a measuring cylinder, and calculate the volume of the statue. Use rho equals m divided by v. So remember, rho means density, so we've got density as mass divided by volume to calculate the density. I always put in a step to get valid results. So something that the experimenter has to do to make sure that their results mean what they think they mean, and that expression is valid results. So I've just dropped in an easy one here because they've given me no indication that that's super important, but I always put it in because I know it's likely to get me into that top bracket, that 5 or 6 out of 6 brackets. So I said to get valid results, ensure that all the water is collected in the measuring cylinder. So let's go to the mark scheme, which is here. So measure the mass using a balance, calculate the density using mass divided by volume for both. For the metal cube, measure the length of the cube size using a ruler and use it to calculate volume. So I got all of that. So the small statue, immerse in water, measure volume, mass of water displaced, volume of water displaced equals the volume of the small statue. So all points that I've raised. Okay, so if you've basically said a few things you can measure, you get 1 or 2 marks. If you manage to explain how to get a clear description of one of them, but you've missed out some steps in the other ones, or your steps are a bit jumbled, you would get 3 or 4 marks. To get 5 or 6 marks, you need a clear and coherent description of both methods. So coherent just means that the marker can follow it step by step and understand each step and how it's done. You need the equation for density. It needs to be logically ordered, and do you see how my numbered steps really show logical ordering and could be followed by someone else to obtain valid results? So you can see that because I put in that last bit about valid results, I would definitely be up there. I would definitely be in that top bracket. Okay, so numbered steps, something to get valid results, and using the imperative, measure this, record that, place the statue in the displacement can, collect the water. So you're talking in really simple instructions. Last question. You're doing really well. Here we go. Question number 7. When the gas in a container with a fixed volume is heated, the pressure increases as the temperature increases. Explain why the pressure increases. Use the model in the figure above to help you. So there is no model in the figure above, so that's a bit weird. So key thing to remember is when the temperature of a gas increases, what that means is on average the kinetic energy of the particles is increasing, and that means that the average speed of particle motion in the gas is also increasing. So if particles are moving around quicker, what that means that they will do is they will bump into the walls with more force, and they will bump into the walls with a greater frequency. So in every second for a hotter gas, you will get more particle collisions with the walls than you would in a cooler gas whose particles are not moving around as quickly. So if you have a greater force because you've got a greater number of collisions, in a given amount of time and a greater force per collision, you will have increased the pressure. So, at higher temperatures, particles have more kinetic energy. Average speed of the particles increase. So there'll be more frequent collisions with the walls of the container, and that applies a greater force on the walls of the container, so the pressure rises. Okie doke. Thanks very much. Well done, and you know, keep going. I know it's hard. It's a bit weird doing everything remotely. Well done to those people who are giving it a go. Okay, you don't have to get everything. Remember, everyone in the country is struggling remotely, but if you're trying to do each activity, remember you can email me for help. You can email me when you're not sure of stuff, but do just keep trying, because if you try when other people give up, you will beat them, you will outperform them when your time comes. Alright, so well done, and goodbye.